Hello, everyone. My name's Harriet. I'm Senior Operations Manager here at Decarb Connect, and it's my pleasure to introduce to you today our November webinar, this time in partnership with Svante. So in today's discussion, our team of experts are going to be talking about how next-gen carbon capture solutions are advancing decarbonisation across multiple sectors. And within this, they'll be doing a deep dive into Svante's journey from startup to commercialisation. Now, before we go into that, there's just a little bit of housekeeping from me before I pass over. Q&A. Please feel free to share any questions that you have in the Q&A box below, and let us know if you'd like to direct your question to anyone in particular. Our speakers will be answering your questions in the final 15 minutes of today's session. Please just say who you are with your email when asking if we don't have time to answer. So a quick round of introductions are in order. I'll first hand over to Vrashali to introduce herself.
Thanks, Harriet, and thank you everyone for joining us. My name is Vrashali Revankar. I'm a project development manager at Svante. By background, I'm a chemical engineer with an MBA. My experience spans across pre-feasibility and feasibility studies, low carbon technology, techno-economic analysis, and also navigating the policies that impact them.
Great, thank you. And next up, Linnell.
Good morning, everybody. My name is Linnell Pereira. Very happy to be here. I'm the Director of Product Development. I've been with the company for now a little over 4.5 years, also a chemical engineer by trade.
Thank you. And last but not least, Philip.
Hello, everyone, and good morning. My name is Philip Cross. I'm the Senior Process Specialist here at Svante Carbon Capture. I've been in the carbon capture industry for many years. My background is in chemical engineering, as well as a PhD in biosystems engineering. Thank you.
That's all from me for now. Over to you, Vrashali.
All right, so who is Svante? So Svante is named after Nobel laureate Svante Arrhenius, the scientist who first predicted climate change over a century ago. So we've known about this for a while now. Today, we are a leading carbon capture and removal technology provider. Started from humble beginnings in a garage, we've grown to over 18 years of innovation with approximately 140 patents and partnerships with industry leaders like Samsung and BASF, because tackling climate change requires collaboration like all other industries. So our business spans three main units. The first one is the original equipment manufacturing and design. So this unit develops our nano-engineered filters and rotary contactors that are at the core of our solid sorbent technology. Next, we have our solutions and digital services. So this is where me and my fellow speakers belong. We provide end-to-end lifecycle support from pre-feasibility, feasibility studies to FID and beyond. With over 75 years of combined experience, we partner with EPC contractors such as Kiewit, transportation and storage providers, and equipment manufacturers to deliver tailored solutions. So two of our capture solutions are the Veloxotherm solid sorbent process using metal organic frameworks. This is a physical adsorption. And the second one is the OAS Blue liquid amine technology licensed from BASF. For today's webinar, we'll focus on the solid sorbent technology. Apart from this, we also offer a plug-and-play concept called Credi. So this is for modular design, and I'll talk more about that eventually. Finally, we also have the Svante Development Company. So once the project is technically sound, this unit helps the project succeed commercially. So they provide project advisory and carbon market expertise, including financing support, carbon credit monetization pathways, and offtake relationships with credible buyers. So they also assist with CO2 transport and storage solutions. And overall, altogether, we help the projects move from concept to reality. Okay, so before we dive into the technology aspects, let's look into what are some of the challenges and opportunities in the carbon market. Right, so the first challenge that we all are aware of is the regulatory uncertainty. Policies often feel like they take two steps forward and one step back, depending on which country you're looking at. So, for example, in Canada, a province recently cancelled its industrial carbon program, and yet on the other hand, the federal government's 2025 budget indicates that the carbon capture investment tax credits, full credit rates have been extended by 5 years beyond 2030. So you see, that's what I mean by two steps forward and one step back. So, in contrast, the EU offers no direct subsidy programs for CCUS, relying almost entirely on emissions trading system and funds like the Innovation Fund. There's also challenges around the carbon market pricing and demand. So volatility is a major issue, as we are aware. So prices depend on the supply, the demand, the credibility of the credits, and the durability of them. So all of this combined together, many markets have fallen below the levels that make CCUS projects viable. But there is still hope. So this slide shows how carbon capture projects can tackle these challenges. The key takeaway here is the diversification. So projects don't rely on a single source of revenue or income, but a combination of different parameters like the tax credits, the grants, and carbon markets to improve economics and reduce the risk. The pie charts you see here represent different programs for particular regions. So, and the percentage that you see is the value contribution of that particular program. So, for example, if you look at the top left corner, biogenic projects based in Alberta, Canada, can tap into the federal program ITC investment tax credits, as well as Alberta's carbon capture incentive program. And there's also the option of tapping into the CDR market, which is the carbon dioxide removal market, the voluntary carbon market. And these can have contracts running from 10 to 15 years. So that's one of the ways how projects can diversify their income sources. On the top right corner, we see the US. So US model it's comparatively much simpler. Majority of the credits come from the income comes from the CDR market. You can see the 73% of that. And there's also, it can be clubbed along with the 45Q tax credits, which support projects for over a period of 12 years. The bottom line here from this slide is diversified revenue streams such as credits, tax incentives, and grants. These are essential for making your CCUS projects economic. Now, let's move on to what Svante's technology offerings are. So first, we've got our solid sorbent technology using metal organic frameworks. So this process uses physical adsorption, where CO2 molecules attach to the surface of the MOF without a chemical reaction. Second, we've got the OAS Blue Liquid Amine solution. This is licensed from BASF. While we bring our experience with carbon capture and know-how on integrating it with your site. So this process is a chemical absorption where CO2 reacts with the amine to separate from the flue gas. Now, why do we have two options? It's because flue gas composition and site conditions vary. So our team evaluates each site and selects the best technology for your needs. For today's webinar, as I mentioned earlier, we'll be focusing on the solid sorbent technology. Now, what is MOF? Imagine a sponge that absorbs water. It doesn't react with the sponge, right? It just holds the liquid. Similarly, MOF, or metal organic frameworks, is a porous crystalline material that absorbs CO2 molecules on its surface. And the MOF that we use is called CAF20. It's known for its exceptional CO2 absorption capacity and stability. It's at the heart of Svante's technology, backed by decades of research and scientific experience. And more recently, we are also proud to say that CAF20 was featured in the Nobel Prize for Chemistry as an example of MOF's groundbreaking performance in CO2 capture. Now, why is this a step change in our carbon capture industry? So to give you some perspective, 1 gram of CAF20 has enough internal surface to cover an entire football field when unfolded. So this huge surface area means more CO2 can be captured efficiently. The image you see here is our filters coated with MOF. And unlike chemical adsorption, this process is physical, as I mentioned, so that makes it highly energy efficient. It's also inert and therefore resistant to flue gas contaminants and, importantly, non-toxic and environmentally safe. CAF20 also has a very low thermal mass, meaning it heats up and cools down quickly. So that allows fast startup, load following, and lower energy use compared to traditional methods. So these properties make MOF a game changer for scalable and cost-effective carbon capture. On this slide here, you see how the entire technology itself. So starting from the left to right, the filters that I showed you earlier are stacked onto a cartridge, which is then loaded into a rotary contactor. So this rotary contactor uses our veloxotherm process, which is a rapid cycle temperature swing adsorption process. It has three main sections. The first one is the adsorption of CO2. Next is the release of CO2 using low pressure steam. And finally, filter regeneration. Now, all of these three occur within one cycle. And the best part of this is that the entire cycle just takes 60 seconds. So that speed combined with low thermal mass and steam-based regeneration makes the process highly energy efficient and environmentally safe. Now, let's move on to how and where these filters are actually built. So we recently launched this facility for manufacturing of filters. These filters, it has a capacity of manufacturing up to 10 million tons. Well, it doesn't manufacture the CO2, but it manufactures filters that can capture up to 10 million tons of CO2, which is equivalent to removing 2.7 million gas-powered cars from the road. And you can see here the facility is automated. It's got the robotic arms putting the filters together. This is also where we successfully scaled MOF from a few grams to tons of MOF. So if you plan to visit Vancouver anytime, we're happy to give you a tour of our facility so you see it in person. Next, we have the commercial scale contactor. This contactor is actually located at our site here. So it's called the Buck. And if you look at it closely, you can see it rotating. So this was commissioned in-house for in-house operation back in 2023, and we use it to test and optimize the actual contactor itself. So meaning the mechanical design, the rotation, the seal testing, etc. So we use this to continuously optimize the design limits. And finally, well, not yet, but the URSA that you saw previously, that's the URSA 1000. And these come in two main sizes. URSA 1000, which is capable of capturing up to 500 tons per day or more, depending on the concentration, and URSA 2000 that can capture 2000 tons per day or more. So the main difference between these two is the diameter and volume of the filters. And finally, we have Credi. So we've partnered with Samsung ENA to deliver a carbon capture model that is pre-engineered, modular in design, and ready to go. So Samsung ENA complements this with its advanced engineering data platform and years of EPC experience building standardized packages where each module, for example, the contactor is one module and the balance of the plant could be separate modules. So all of these modules are pre-engineered, transported by trucks, and assembled on-site like building blocks. So together, this reduces capital expenditure compared to stick-built models, shortens project schedules, and allows customers to deploy carbon capture with minimum disruption at site. It's truly a plug-and-play concept. To know more about this, feel free to scan the QR code. Just giving you a minute to scan the QR code. All right, over to you, Linal, to cover how our technology is commercial ready.
Thank you very much, and very happy to be talking about our commercial-ready technology with you today. Next slide. So on this slide here, you can see our lab scale design, which was used to validate our technology from 2016 through to 2019, allowing us to achieve a technical readiness level, or TRL, of 4 and 5. What's really important to understand here is that our filter length is what sets the performance of our filter beds. And this filter length has been consistent in these lab scale designs that you see here, all the way through to our pilot and small scale demo that I will be talking about shortly, in continuing further to our commercial scale design that we're in various level of engineering today. This allows us to continue to build off of the data that we've collected over years and years of operation to both validate and de-risk our technology. Next slide. So the first demonstration plant that I will be talking about today is our Synovus 30 ton per day that is in Saskatchewan, Canada. This was on a once-through steam generator, or OTSG, and it started operation in 2019, accumulating almost 19,000 hours of operation. before successfully completing its test campaign in 2024. Next slide. Here you can see our Chevron demonstration plant, which is at 25 ton per day. This is at their California facility on their natural gas boilers. This has been in operation since 2023 and as to present has accumulated almost 4,000 hours of operation. What's unique about this facility is we are able to simulate various different CO2 concentrations on the inlet to demonstrate our filters capabilities for different industries. Next slide. And lastly, our smallest pilot, which is on the Lafarge, now owned by Amrice, cement kiln in British Columbia. This has been in operation since 2019 and has accumulated almost 13,000 hours of operation. Unique to this facility as well is the ability to simulate various different gas compositions to demonstrate our cycles for commercial scale projects for various different industries. Also, for those who are not aware, cement processes have a higher degree of contaminants, which pose a different challenge for capture technologies. So not only are we able to showcase our performance in cement, but we're also able to showcase the stability of our adsorbent in real cement gas. And this will be taken further in the next slide. So this is a data snapshot for the purpose of this webinar. We chose to highlight specific data sets so it's easier to follow the messaging that we're trying to show here. Here is one filter set's operation over the course of 7,000 hours. In the green, you can see the product purity, and in the blue, you see the recovery rate. Initially, you can see that we're not only able to meet, or we are able to exceed in some cases, the target performance that we were looking to achieve within this test campaign. Most importantly is through continuous operation of up to 7,000 hours, we do not see any degradation in performance. We are able to maintain our performance over each parameter over the course of this test campaign, which is how we validate that the filters themselves are stable to the contaminants that are in the flue gas that we see in this pilot plant. Next slide. Recently, we were able to commission our mobile demonstration units. As the name suggests, these are units that we're able to locate to specific flue gases. Recently, we were able to complete our test campaign with Technology Center Mongstad, or TCM in Norway. This is one of the largest testing facilities for developing capture technologies in the world. Through this test campaign, we were able to achieve two goals. The first is demonstrating that there are no secondary emissions from our technology. This greatly streamlines permitting for commercial scale plants. Furthermore, we were able to validate the stability of our filters in real contaminated FCCU flue gas. For those who are not aware, FCCU stands for Fluidized Catalytic Cracking Unit. Tongue twister, and I love that first thing in the morning. But essentially, this comes with a fair amount of contaminants, such as catalyst particulate, NOx, SOx, and aerosols. So this is very much no small achievement, especially for the oil and gas sector, this is one of the major emission sources for any given refinery. Next slide. At present, Svante has 2 MDU units that are available for testing at your location. While we have sufficient data to showcase and validate our technology and move forward with commercial plants, obviously I am very biased in that, we are happy to bring these units to your site. We recognize that a customer can benefit very greatly from a comfort standpoint in bringing these units to your specific site to not only understand our technology firsthand, but also to learn firsthand the operational simplicity that comes with our technology. So we are very happy to be as transparent as possible in this space. I think that's one of the biggest challenges is demystifying certain technologies and bringing them on site. We are now able to do that, and we're happy to engage with you if this is something that you're looking to understand better. Next slide. So from the small scale, I'll now transition more to the commercial scale projects that we have. First and foremost, this is the Delic US Texas Refinery FCCU capture plant that we have in our pipeline. It is for 145,000 tons per year of CO2 captured. And notably, this is a project that has been selected to negotiate for up to $95 million of US federal funding. Excitingly, it is now also a project that is moving forward into the feed stage, which is, for me, very exciting to see projects move even further and moving to the next stage. Next slide. And lastly, what I'll highlight is our Mercer capture project on the Peace River pulp mill. This is targeting up to 500,000 tons per year of biogenic CO2 from the recovery boiler, which is one of the largest emission sources for this specific mill. Excitingly, in this case, this is now advanced to a pre-feed phase of commercial maturity. In both cases, you can see there's a large amount of work that goes into these projects, but I want to make sure I clarify that these are not the only projects Svante is working on. We are on projects globally, and they're in various phases of development. These are just the fun ones that I wanted to highlight for the purpose of this webinar. Next slide. So I'll wrap up my section by talking about why customers choose Svante. And from the feedback that we've been getting, we see the main drivers fall into a combination of these buckets here. The first is low-grade heat utilization. Because our process is under a slight vacuum, we're able to leverage waste heat sources down to 70 degrees Celsius. This allows us to, through integration at site, to be able to minimize the energy that we require for carbon capture from outside battery limit sources. This has a great impact when it comes to OpEx and CapEx optimization. The next is electrification. Depending on the drivers for a given project, a client, because of the utility availability at site, or because of the overall project dynamics, for example, a low CI product value, may want to switch from natural gas sources to more of an electrified approach if there is clean power available. Within Svante, we are able to showcase those different benefits and have that design flexibility in-house. As mentioned, both in the TCM test campaign, we have proven that we have no secondary emissions from our technology. But furthermore, I want to highlight that our adsorbents themselves are recyclable. So over the long-term operation of our technology, you're not introducing a larger waste stream from spent filters. As I mentioned, both in the TCM and the cement pilot, we have been able to prove our robustness to contaminants. A lot of hard-to-abate processes have high contaminant streams, which challenge various different capture technologies to require expensive pretreatment systems that change the nature of the business case. Within Svante, this is not a concern that you have to worry about. Next is our operational flexibility. Now, I mentioned a few pilot plants, which you are more than welcome to visit if we're able to coordinate, but also this can be seen firsthand with our MDUs. But essentially, we have been able to demonstrate the ease in which it is to operate our system, but also because of our fast cycle, we are able to load follow as well as startup, shut down very quickly. And I'm to put into context, that's within minutes, which is a huge advantage for us in certain operating spaces. At the end of the day, the high purity and recovery targets for given projects is key for maintaining a strong business case. And of course, we need to make sure we deliver here. These advantages have been validated over thousands of hours of pilot plant operations. And realistically, it comes down to a few things when it comes to how much of a magnitude they will have on the project. That really comes down to the site integration, the specific application, and the value drivers for a certain project. And we're happy to engage to showcase our technology and validate whether we have a strong enough case for you. So please engage if you're looking to learn more. And of course, it comes down to the specifics of a site. So I will now throw it over to Philip, who will go into case studies to demonstrate where we are good.
Thanks, Linnell. Thanks for sharing. So the case study on cement that I'll be sharing today is based on an actual engineering study that we completed alongside a client in Europe. We evaluated real flue gas, looking at the contaminants and other constituents, and we were able to use the CAF20 performance characteristics from our pilot units, combined with vendor data of balance of plant to give a good estimate for the performance and cost. Next slide. So the key advantages that we identified through the study were that we had demonstrated the actual performance of our pilot units on similar flue gas. We could show the CO2 recovery and purity, and we could show the steam ratio and bed productivity. We're also able to fully electrify the process. So what this means is that all the steam required for CO2 desorption was produced through our flash steam generation and mechanical vapor recompression systems within our battery limit. So we're not integrated for steam on the site. That gives us a lot of load flexibility on our side. Our MOFs don't produce any secondary emissions, resulting in a cleaner and more environmentally process. And finally, the capture process is easy to operate, so we don't require long startup times to heat solvent, and we can respond quickly to starts, stops, and load changes at the cement plant. So why does this matter? For cement producers, operational flexibility is critical. Plants often face variable loads and maintenance schedules, and Svante systems can adapt quickly, minimizing downtime and maximizing CO2 capture without compromising our production. Next slide. So this slide shows a simplified block flow diagram of a cement plant. It's highlighting where carbon capture and heat integration can take place. In the current case study, we look to integrate at location A with the stack, but I did want to take a closer look at why integration strategy matters, especially under varying load conditions. So cement plants rarely operate at a perfect steady state. They experience frequent load changes due to raw material variability, kiln maintenance, and market-driven productions. So there's a few areas for location. Like I mentioned, there's location A, where you can do CO2 capture. The advantage of this is that there's minimal interruption to the cement plant. You have some flue gas heat that can be used to reduce the energy consumption. Some of the cons are, however, though, that the CO2 concentration can be lower due to possible false air making its way into the stream. You're subject to variations in flue gas during switching between modes of operation. I'll cover a little bit more of that in a second. And you also have, for cement plants, you have relatively low gas temperature as well as CO2 compared to other tie-in locations, such as location B. So this is after the preheater. It's for CO2 capture and heat integration. The pro is that this is a really hot stream. So this is coming off of the calciner where most of the CO2 is produced. So you have much higher CO2 concentrations. However, there's really high dust loading in this. And if you integrate at this location, you're also going to have a greater impact to the cement process. So the stream coming off of the preheater is often used to dry the material. So the last area is at the clinker cooler air. So the advantages here is that the hot clinker cooler air can be sufficient for generating some low pressure steam for CO2 capture, or can be used to preheat raw mill. Again, one of the cons here is high dust loading for it. So the key drivers affecting integration, so tie location. So the flue gas composition can be higher than 25% on a dry basis when taken after the preheater due to no air dilution. So higher partial pressures of CO2 often drive it into the beds, making the system more efficient. Also, raw material characteristics of the mills. So these mills have to dry their material. So the moisture content can change the heat availability from the site, and it can also require additional energy for drying. And lastly, the mode of operation of cement plants. So they can have the raw mill on or off, vice versa. And this can have a significant impact on the air ingress, consequently the CO2 concentration and the temperature of the flue gas. And so the plant age is also a factor that we need to consider when we're looking at deploying carbon capture on cement plants. So older plants can be more challenging to control this air ingress, and you can see CO2 concentrations as low as 14%. So Svante's advantages here, it's our ability to customize an integration strategy. We can work alongside clients to optimize heat recovery, looking to minimize energy consumption, which directly impacts operating costs and sustainability goals. So as I mentioned, for the case study that we did alongside our client, we integrated at the stack. Let's now take a look at this simple integration on the next slide, please. So the cement plant used for this study, we were able to take flue gas directly from the stack and send it to our battery limit. We recovered a little bit of waste heat, cooled it to appropriate temperature, and then sent it into the carbon capture plant. The CO2 product coming off the Svante system went into a single post-treatment unit and then was able to meet the Northern Lights specs. So what this highlights is our robustness to process contaminants, and also, as Lionel mentioned, high CO2 coming out. We're able to meet specs with single treatment, post-treatment options. Next slide, please. So getting a little more into the details of this case study. The flue gas flow rate was 3,000 tons per day. This is roughly 1 million tons per year. This would use 2 of our URSA 2000 units. You can see the design criteria on the left. Of note, 90% recovery. We've also seen studies where we come in and look to do 95% CO2 recovery. Within the ISBL, we have a flue gas blower. We pull a little bit of low-grade heat, and then we send it to a DCC where we do gas cooling. We're then ready to send it into the Svante capture unit. Since our system is not pulling steam from outside the battery limit, we wanted to show the heat integration within our site. So the red dotted lines show the use of low-grade heat that run our MVR system. So this is a vacuum flash system. We're able to pull steam. We're then able to increase the heat of that steam through mechanical vapor recompression. For this site, and for many of our technologies, we're able to use this to be fully electrified and fully independent of the plant for steam use. As we mentioned, the cement plant is undergoing a lot of different load changes. That's also going to affect the steam that they can provide to us. So in this way, we're independent. It gives us a lot of flexibility to meet the needs of the cement plant to maximize their carbon capture goals. Next slide. So with this case study, we were able to see a 0.9 gigajoule per ton CO2 as the total electricity requirements for the capture plant. All the steam was generated internally for our MVR system. The liquefaction process used roughly 0.5 gigajoules per ton CO2. So the total electricity use was 1.4 gigajoules per ton. There are always CapEx, electricity consumption, and level of heat integration trade-offs for cement plants. And this would allow us to drive the number lower if that was our target for the study. As mentioned, we're able to fully utilize heat from any stream 70C and higher. We can be fully electrified, and our team is specialized and has done many case studies on these, looking at ways to meet the client needs. If that's a CapEx or electricity consumption optimization, we have experience doing those studies. And we have real world data from our pilot units to kind of back up how these processes perform. Thank you. Next slide. So our case study in pulp and paper. This is an example where the client was interested in utilizing as much waste heat as possible and minimizing the electricity consumption of the carbon capture unit. Next slide. Through the course of the case study, the key advantages that we identified were the robustness of the MOFs to the contaminants, minimizing pre-treatment needs, leading to a simpler process. Because pulp and paper mills are looking to generate carbon dioxide removal credits, it's critical that the capture plant doesn't have any secondary emissions, and that's an advantage for our technology. In this case study, we're able to maximize the use of heat integration for high and low grade heat. This allowed us to significantly reduce electricity consumption. And then lastly, our dedicated team of project development experts identified pathways for project financing and development in the CDR landscape. Next slide. So similar to the cement plant case study, I wanted to cover a simple block flow diagram of a pulp and paper plant to highlight where carbon capture plants can integrate for CO2 capture as well as heat utilization. So the main location for carbon capture is after the recovery boiler. So what a recovery boiler does is it burns the black liquor. This is mainly lignin from biomass and chemicals. It does this to recover the chemicals to be used in the process. So the CO2 that's generated is highly biogenic. In this case study, we also wanted to integrate with the power boiler stack at location B. So power boilers use a mix of biomass and small amounts of fossil fuel to produce steam and power for the pulp and paper plant. Again, we only integrated with that for heat use. Our system was fully electrified, and we generated all the steam inside our battery limits. Next slide. So this case study, we were looking at capturing 1,600 tons per day. So this would be a little north of 500,000 tons per year. This would be one of our URSA 2000 units. So the CO2 concentration is lower in pulp and paper mills than cement plants. And additionally, the facility required dense phase CO2. So we implemented a compression system and achieved greater than 96% purity at 150 bar. Since we had more heat available in this case study, we also implemented waste heat recovery and steam generation on the flue gas coming from the power boilers and recovery boilers. Also, because we use a compression system, we could take some of the heat from there as well. This allowed us to cut back on the amount of steam generated from the MBR, reducing overall electricity consumption. Next slide, please. The results of this case study on pulp and paper showed a significant reduction. So we're able to get the electricity use down to 0.23 gigajoules per ton of CO2. This was through the use of high and low grade heat integration that we implemented. The compression system with heat integration uses slightly more power than the previous liquefaction unit in the cement case. But overall, with the system, we were able to drive down the electricity consumption to less than 0.8 gigajoules per ton of CO2. We're also able to show annual CDR revenue of 80 to 95 million and really highlight the advantage of our moss-based capture technology. So in short, Svante delivers a solution that is energy efficient, environmentally responsible, and financially attractive, helping our clients turn carbon capture into strategic advantages. And with that, I'll hand it back to my colleague Varashali to summarize why you should choose Svante to help manage your carbon emissions.
Thanks, Philip. Just to summarize, our technology is proven over years of testing and piloting across industries. The solid sorbent technology is simpler to operate, it's robust to contaminants, and depending on your flue gas conditions, we also have a plug and play concept ready for deployment. If you would like to explore this further, our mobile demonstration units could be on your site next. So contact us today to tackle your emission reduction targets. Thank you. All right. The first question here is, who are the top 3 carbon capture competitors globally? Okay, the top 3 that I can think of are Carbon Clean. There's Carbon Clean, there's Acre Carbon Capture Solutions. There's also the Mitsubishi MHI carbon capture technology. These are the top 3 that I can think at the top of my head. And feel free to jump in, Philip, Linnell, if you want to add anything.
Outside specific companies, I would think largely it's technology decision driven. So you will see HPC in the space, amine, cryogenic, membrane. There are various companies that come into competition across projects based on their client relationship or what they're willing to demonstrate at site or the fit of the flue gas. I have not seen consistency in terms of specific companies, but I've seen consistency in the types of technologies we compete against.
Thanks, Linnell. So there's also a question, how do you differentiate from carbon clean solutions and technology? So carbon clean, if I remember this correctly, I'm not an expert at carbon clean, but so if I remember this correctly, they are an amine-based solution. And compared to that, we are a solid sorbent technology, which is a dry system, and also it's a physical adsorption, so much more energy efficient. And our technology does not have any secondary emissions, and those are what I can think of. There's a lot of difference because the carbon clean technology it's a liquid-based amine system versus this is a dry system.
Yeah. So amines are they've been kind of developed for gas processing, really looking at low partial pressures of CO2. They've really excelled in those reductive atmospheres. They've been looking to transition into the post-combustion capture space, largely in the power market off of gas turbines, where you typically have much lower concentrations of CO2, like 4% is pretty common for a gas turbine. So you'll see projects being deployed really in the power sector that look to use amines. The CO2 concentrations that we looked at today in our case studies were much higher. So they're 14 to over 20%. And that's where our MOF-based system really excels and really starts to have advantages because, we've got the really, really high surface area we can load a lot of CO2 per space with our system. So the beds are quite short. We don't have to continually increase our liquid to gas ratio because we don't have one, which amines would have to do as that CO2 concentration goes higher and higher and higher. So we have our two size systems. We've got the URSA 1000, the URSA 2000. Those are our two systems. We can stack them together for larger facilities. But amine systems, they usually have to get larger and larger as the CO2 concentration gets bigger.
Thank you. So the next question is, do emitters need to have low pressure steam already available on site, or do you offer waste heat recovery technology? Linnell, do you want to take that one?
Sure. So you do not need to have low pressure steam available at site. Obviously, that is very cheap if it's already there, but it's not a requirement. As I mentioned before, site integration, especially for the viability of a project, is very key. How we leverage waste heat sources, and we can have that within our design scope. We're happy to do that. To explore that a little bit further, because I see some of the chats talking about cost per ton. What we typically do is, because site integration can very much change how a project looks economically, even with the same technology. We typically look for initial information from a site, what utilities are available, what waste heat is available, composition of the flue gas, and we will run an initial study, what we call a FEL0, to frame up the capex and opex associated with our solution, whether that is the amine or the MOF itself. And from there, the client can then decide whether we are a fit to go forward, and then go from there. But it's not a requirement. We can come up with a very large list of alternatives to move a project forward. I think we've seen pretty much every variation of site and what they have. So we have options to explore.
Okay, the next question is, what is the ultimate fate of the CO2 molecules that are captured by the filter beds? So that really depends on what do you want. So there's different options. You can either sequester it underground, you can use it for enhanced oil recovery where you route it through to other wells, older wells. There's also products that you can generate out of the CO2. So it really depends. Like you could convert it to a sustainable aviation fuel, or yeah, it really depends on what your goals are for your project. So, and also what is the storage site available near your location and the transportation available. So there's a lot of different factors that go into it. But yeah, so ultimately it's what's the lowest hanging fruit for that CO2 molecule. It could be either sequestration or conversion utilization. It could be either of those. Okay, so there's another question. How are the feed and pre-feed studies funded? Are these paid by the interested companies, or are there other sources of funding available for industrial partners interested? Linnell, do you want to take that?
Sure. So, like with many things, the answer is complex. But to simplify it, there's a spectrum. It can be as simple as a one-to-one with the emitter looking to move forward on their specific project and move quickly, and they have the budget and the strategic alignment of this is what we're going to do, in which case it's fully funded by the emitter. There are examples, like I mentioned, with the Delic project, where there's federal funding, and certainly we have projects in Europe that look to leverage either the innovation funding or reverse auction to support these projects moving forward. But notably within Svante, what's unique for us is we have our development branch of our company, which Vershali mentioned at the start of the presentation. This can help bring forward capital to move a project from different levels of engineering. So lots to talk about, and happy to engage on a project, a specific conversation if that's what's needed to move forward.
All right, there's a few questions on the lowest concentration and the concentration of CO2 treated. So that depends on, so we have the two offerings, right? So there's the solid sorbent technology and the OAS blue. So depending on what your concentrations is, if it's like above 12% or so, then the solid sorbent is a great technology to use. And for lower concentrations, we have the OAS blue as an alternative. Then does Svante provide fully electric package of technology? Yes, we do. And Okay, the next question is, how is the workflow if we want to get a mobile unit for our site? Linal, do you want to take that?
Sure. So I would say to piggyback off what I said before is the first thing we would like to do is a fill zero to prove what we look like on paper with the data that you provide us. If that is something that's viable, if there's a fit from a business case from your perspective, then there is a need to continue a conversation of how do we de-risk and make you more comfortable with our technology. The MDU could facilitate that. And from that standpoint, there's a whole stream of activities that go into that. But the first step in my mind is showing that we're the right fit. We're not looking to just put the MDU everywhere because there's way too long of a list of people that would love to have the MDU at site if that was the case. We're very focused on leveraging the MDU to move forward with commercial projects. So that would be the first step, and then after that, there are activities that we're happy to support to move it to your location.
All right. So there's this question on what is done with the materials that come out of the filter, especially if toxic, and what sort of tonnage do the three cases generate? Presumably, this is dumped to the atmosphere without your system. So if I understand this question correctly, what is done with the materials that come out of the filter? Well, first of all, it's not toxic. It's non-toxic material. So and the material itself can be recycled. And yes, right as of now, it is usually dumped into the atmosphere. So, which is why we're implementing a carbon capture system is a great way to reduce your emissions.
Yeah, I'll add to that.
Yeah.
So, kind of the big ones there are generally your SOx and NOx systems. So flue gas is generally quite hot, and what you're managing there is kind of the acid condensation point. And so we'll look to manage that for our system, and we'll pull those out kind of in a liquid stream that can be neutralized and sent to a wastewater treatment facility and managed, so it doesn't get released into the air that way. Um, we don't have to do a lot of that with our beds because they're tolerant to contaminants. So a lot of them pass through our beds and they'll come out into the stat gas. We do significantly reduce PM and other acid systems just in the general DCC that we have there. So we are reducing other pollutants as well as CO2 by implementing carbon capture systems.
All right. So there's also a question on Philip. I think you can take this one as well. Hi, thanks for the great talk. One question regarding the electrification for regeneration. Is the electricity used to generate steam, or are there concepts to utilize the electric energy directly? By Florian.
Yeah, so we do need the steam for our CO2 desorption. We do have a moisture swing component, so water does help move the CO2 out of the beds. So we can't simply electrically heat the beds. We predominantly use MVR, which is vapor recompression. That works well with us because we have a vacuum. So we can flash warm water at really low pressure, which will give us vapor. And then as we run that through compression, you'll pick up heat, and then we can use that in our system. So we do not currently have a fully electric heated system. We do use water in our process.
Okay. And then there's also a question on, is Svante technology compatible for emitters with fluctuations? Lina, do you want to take that one?
Sure. And I'm assuming when you say fluctuations, you are either talking about CO2 concentration fluctuations in the inlet or just process variability in the flow of flue gas. In both cases, I would say we are very compatible with that. As I mentioned, our process being 60 seconds allows us to load follow very easily and make those certain adjustments to changing inlet concentrations or changing inlet volumes. We've been able to prove that within our pilot plant with Lafarge on the cement kiln. That's happened several times. And of course, over the course of various other pilot operations, we've been able to showcase that as well. So happy to be transparent around on how that looks.
Okay, so we have a question on how important is it to remove dust from the flue gas before inputting it to MOF unit in case of adding to coal or waste fire power plant. Philip, do you want to take that one?
Yeah, definitely. So the beds are can tolerate quite a bit of dust because they have spaces between them. So it comes down to sort of a particle size distribution. We do have specifications for total loading, um, but again, so dust, particulate matter can generally be classified into two main categories. There's usually condensable and filterable. In the pulp and paper industry, a large part of the dust is condensable. And so as you go into a DCC, that dust isn't necessarily difficult to remove. Some of the filterable material, that's where the robustness of our beds really shines. Small PSD, and small loadings is something our beds can handle.
There's also a question on, Philip, I guess you can answer this one. Are cooling towers a must when integrating Swante's technology with a pulp and paper mill?
So they can be cooling towers or air coolers. We do cool the flue, we do need to cool the flue gas down to, below 40 C for the absorption step. We have there are two phases, right? You have an absorption and desorption. So one is exothermic, the other is endothermic. So that exothermic reaction is going to run better at a little bit lower temp. So we do need to cool it down. We can use wet cooling, hybrid, or air cooling for that system, and we can go to full air cooling. So we don't need wet towers to run the system.
Okay, there's one more technical question here. Does Swante technology require deep drying of flue gas? Asking because many MOFs are sensitive to flue gas water.
It does not require, so we don't do any upfront drying. Basically, just the once you cool the flue gas down, we'll reduce it below the adiabatic saturation temperature, so you'll get some natural condensation out, but we don't have to do any additional cooling. As I mentioned, our system is very tolerant to water, so we'll actually use steam to desorb. So um, that's for the desorption step, and on the absorption, um, no, we have moisture coming into the flue gas into the beds.
Okay, there's also a technical question here. Swante understands both amine-based as well as their flagship MOF technology. And moreover, from the case studies, the raw energy demands for these two processes. So ignoring the considerations of MVR, site integration, etc., one would imagine that the steam requirement for physical absorption with MOF would be less than that of an amine-based. How do the two raw steam requirements compare on a per ton removed basis, as well as the steam demand? How do the steam qualities pressure compare?
Yeah, I mean, so for total steam demand, amines can be quite efficient, depending on the CO2 concentration. So I mentioned at really low levels, amines are quite efficient, but the loading of CO2 to amine, that scales with CO2 concentration. So when you start to get into higher and higher CO2 loadings, the steam demands become closer. Really, what our system has an advantage of is that we use lower pressure steam. So the energy required to produce that through MVR has advantages over an amine plant. So amine plants, those are 2 to 3 bar, 130 C. We generate our steam under vacuum. So that's kind of where we can see some energy savings for our process as far as steam use. As far as kilogram for kilogram, I'd love to run a case study. Now, we look at both amine and MOF, so we can run those studies for a site if you're looking to compare those two solutions.
There's a question from Salman. Please feel free to have a look at our website for any opportunities, job opportunities. It's all there. And also, you can reach out to us. There's also another question on the energy penalty of point source carbon capture. Philip, do you want to take that?
Yeah. So there we are using electricity as I mentioned, If we look to make use of the waste heat that's on site, that can be somewhat minimized. But you're doing a lot with the CO2 capture plant. So you're reducing the dust that's emitted to the environment. A lot of times those can be different chemicals used in the pulp and paper mill, or they can be different chemicals used in the cement plant. So you're reducing dust loadings. You're reducing the amount of acid gases like SO2 that are released in the atmosphere. So you're doing a lot more with these systems in CO2. So there's a lot of environmental benefits to this. And then, depending on where the development of CO2 utilization goes, this is creating full value chains for CO2 to be potentially fuels and other uses.
Right. Okay, so there's a question on how large a footprint is required for your 2000 unit. Lina, do you want to take that one?
So the 2000 is at 24-meter outer diameter or 24-meter diameter. What I would say as part of the Fell Zero that we do, it's not only just to frame up CapEx and OpEx, but also to roughly frame up the footprint at site to make sure that we can even fit. Uh, with many site integration aspects, a lot of it comes down to the balance of plant requirements, both for post-treatment, liquefaction, um, on-site storage for tanks, depending on if the downstream TNS involves rail. So framing up all of that, it varies across the board. So we're happy to do that evaluation and provide you specific numbers.
Thanks, Linnell and Philip. So I guess we're at the end of our Q&A time. Over to you, Harriet.
Thanks, guys. So yes, that brings us to the end of the webinar today. Thank you to our speakers for sharing your insights, and thanks to everyone for joining us today. We will be sharing a recording of this webinar with you in the next week, so keep an eye on your inbox for that. And please do email me at harriet@decarbconnect.com if you've got any questions about this presentation, or if you're actually interested in hosting your own webinar. Also, bringing things from the digital realm into real life. If you're interested in attending our North America conference in Houston on February the 10th and 11th, we currently have a Thanksgiving discount with $200 off all tickets that ends tomorrow. But if not, we'll see you again at our next webinar. I hope everyone has a great day. Thank you again, and goodbye.